Hello, welcome. This is question 4 for AQA's A2 physics. To remember that then. Yeah, it's probably a little bit difficult there, yes. Anyway, okay, so I've drawn both parts of the question on the board, okay, but obviously that's just because I couldn't be bothered pausing the video and then going over, and there's not that much really in this section, so I think I've done a pretty good job. I'm quite impressed with my art skills there. However, this first part, 4A's, I think quite difficult. I didn't get it when I did the exam, so as a mock, obviously, but I think maybe it's a little bit too difficult for me to get. Anyway, okay, so what we've got here is we've got two coils wrapped around this iron bar, okay, so it's obviously going to be something to do, and we've got a circuit here, and with a fixed resistor, variable resistor even, sorry, and it's obviously got a battery, so therefore we've got a current through here. Basically what this is very similar in theory to a, I think of the word, transformer, okay, in the fact we've got an iron core essentially, and we've got an electric current here going through this coil, okay, and it's going to obviously transfer to the other coil, giving this ammeter a reading, even though it's not directly connected to this battery, okay. So it says now actually one second. Yeah, a centre zero ammeter, by the way. I did have a look just to make sure this doesn't kind of make you go, what the hell was that? Did have a look at what a centre zero ammeter was, and it just means, well, zero is at the centre. So basically, what it means is, basically this is at zero, okay? So it's kind of key in the word centre zero. So it can be minus, so going the other way, so it can read positive and negative currents, if that makes sense. Okay, so that's what that means. I mean, I'm fairly sure you knew that anyway, but it's just a bit of a note to that. Okay, so it says for 4A part 1, initially the variable resistor is set to its minimum resistance, and switch S is open. Describe and explain what would be observed on the ammeter, okay, when the switch S is closed, okay, so quite clearly there's going to be a current going through P, okay. This is therefore going to induce a current, okay? Now because it's going to be an alternating current, okay, it's not going to be, the ammeter generally reads, it's a constant value, it's direct current. Whereas this doesn't, okay, it's going to be an alternating current, okay? It's surely what it's going to result in, okay? So once the current goes through, it's going to go through, cut through the magnetic field, okay? And therefore it's going to induce an EMF in this, okay? But because remember this is a centre zero, so the word they've used is deflect, okay? So basically it just moves away, gives a current reading, and then we'll go back to zero, okay? So there's the first point you need to mention. So it says, the way they worded it, it says meter deflects, then returns to zero. Okay? The current produces, as I say, then you just need to explain what I mentioned, okay, about the fact that as the current it's basically, I think they've done it the wrong way around, okay. So actually what I would do is maybe state that last, sorry about that. So just talk about the fact that it's going to induce the current, okay, it's going to cut through the magnetic field lines, the magnetic density, see how that works. It cuts through the field lines, okay, which induces a current in the coil Q. Okay, so again, just like a transformer would, and then obviously because this is a centre zero, you just say it gives a reading or it deflects, and then just returns to zero. Okay, so that's what you need to just state. Okay, so you just need to explain how it happens. Okay, so there's obviously the current in P. So there's a current in P, in coil P. Which means there is now an electric field round this magnetic field of the iron bar, okay, which obviously causes cuts through the field lines, okay, and causes the current in Q, okay, which causes the electric field lines, field and magnetic field lines to intersect, causing a current in the Q, okay, field lines to create a current in Q. Okay. Yeah. So now you just need to mention that's induced EMF. So that's your 3 marks. So kind of self-explanatory, but a bit weird. Okay. The way, I don't know why it just hasn't listed it in a normal way as a transformer. Okay. So basically that was a transformer question, but wasn't so obvious. Okay. Then it says with switch S closed, the resistance to the variable is suddenly increased. Variable resistor, sorry. It's suddenly increased. Observe what is now observed on the ammeter compared to what was observed in part A. So basically, what it's saying is this is resistance. This is increased. What happens as a result of to this, okay, to the ammeter in comparison to what happened in the previous little part of 4A. Okay, so you need to say what happens and then relate it to what happened in the first part of part A, okay? Now, because there is a increased resistance, okay, there's going to be a lower current, okay? And let's assuming, obviously, the potential difference of the battery stays the same, etc. So, therefore, the meter will deflect in the opposite direction, okay, than P, okay? So, if than in A part 1, okay? So if you just said it deflects to the right, okay, in A part 1, which is totally acceptable, then you say this now deflects to the left, or you just say it deflects in the opposite direction to when it had a very low resistance, okay? So that's the first point you make. And then you say, because there's a low resistance, it's going to cut through the field lines less, if that makes sense. It's going to produce a smaller electric field, so there's going to be less electric field lines, so it's going to get cut through less magnetic field lines, so therefore less current is induced, okay, so it's not going to deflect as much, okay. So there are 3 points you need to state, okay. So as I say, the first one is about the meter in the opposite, so the ammeter deflecting in the opposite direction. Okay. Yeah, so the ammeter deflects in the opposite direction, and this is because, as I said, there's less electric field lines, okay, because there's a small current, or they're not as strong, okay, so they don't cut through as many. So, for saying that, you could just say the field or flux is reduced. Okay, which means there's a smaller EMF in the in the coil P. Okay, so therefore it's not deflected as much. It's deflected in the opposite direction, but it's not deflected as much as it was in part 1. Okay, so that's 4A. 4B. Okay, so what we've got here is we've got a coil. Okay, so it's a very standard question. Okay, and we've got a 40-turn coil of cross-sectional area 3.6 times 10 to the minus 3 meter squared, and a magnetic flux density of 0.42 Tesla. Okay, right, so he's asking for the magnitude of the magnetic flux linkage in the coil. Okay, now magnetic flux linkage is just the same as total magnetic flux. It's equal to N phi, okay, which is equal to NPA, but because we have to take into okay, so therefore we don't have to do anything else with that. We've got N, we've got A, and we've got B, okay, so we just simply sub it in Okay, so no, I thought this was 1 because I didn't see it, but there are loads of little coils inside this, okay, so that's why M is 40. I just put M as 1, that's why I got it wrong. Anyway, so it's 40 times 0.42 Tesla, okay, times the area, which is 3.6 times 10 to the minus 3 metres squared, okay, so just in case of subbing them numbers into your calculator, and you should get 6.05 times 10 to the minus 2 WB terms. Okay, so that's your answer for part 1. Part 2 says the coil is rotated through 90 degrees in a time of 90 seconds. Determine the mean EMF in the coil. Okay, so there are a couple of ways you can do this, okay? But the way that I did this, okay, so this is the equation, one of the equations off of the formula sheet, okay? So the induced EMF is equal to BAN times the angular speed times the sine of the angular speed times the time, okay? Times how long it's been, okay? Now to work out the angular speed, it's 2 pi over the time period, okay? Because obviously that's what we're going to need to work out given everything else. It's 2 pi over the time period, but we're not given the time period. Now it's crucial to remember, as I say, the time period is the time for one complete cycle. Assuming it's going to be moving at the same rate, it's not increasing its speed, okay? It's going to be keep going around in that circle at the same rate, okay? So if it's gone through, if it's taken 0.5, just take that long, 0.5 seconds to go through 90 degrees, obviously full turns 360. Okay, so therefore you need to times both sides by 4, obviously, so therefore you get the time period as 2 seconds. Okay, so now you've got the time period, as I say, it's just logic, that's why I told you that. Okay, so again, it's just a case of subbing numbers into the formula. Okay, so you get E is equal to, we're assuming it's the same as before, so everything else remains the same. So the magnetic flux density, still 0.42, times the area, which is still this 3.6 times 10 to the minus 3 meters squared, okay, times n, which is 40, times the angular speed, well, it's 2 pi over t, so you just put 2 pi over 2, which is obviously just pi, okay, times the sine of pi times t, because the angular speed is pi, because it's 2 pi over the time period, 2 pi over 2, so it's just pi. Okay, so you sub them numbers again into your calculator, you should get 0.12 volts. Or 0.12 watt. Okay, so that's really quite simple. There's nothing too difficult. I think that's a bit easier that. But as I say, if you didn't recognise the fact that that was 40 turns like I did, and I just thought it was 1 because I didn't read the question properly, you lose quite a lot of marks there. But it's out of 9, okay? So, I mean, this was kind of a bit weird. I think the thing with this was spotting. It was like a transformer, okay? And then this was kind of just applying it, really. I say, I'm pretty sure I wouldn't have got that, and I don't think I've done a good enough explanation. But this part is definitely a lot easier, it's just using equations, okay? And again, bit of logic, realising, well, why has it told us it's gone through 90 degrees in 0.5 seconds? We're going to have to use that, okay? But as I say, it's nothing too difficult, alright? So thanks for watching, and we'll see you in the next question or video, whatever you decide to watch.